Log on, tune in, find out. Another good idea from Cambridge.
Welcome to Newton Institute. This week has been unofficially called Tipping Points Week because we're going to have a number of talks on tipping points, not because we're about to all fall down, I think. And we're going to start off with a talk that was actually scheduled prior to that week, but it actually fits, I think, quite nicely, we'll see, from Sebastian Reich, University of Potsdam, on predicting the unpredictable, combining models with data. And I guess we're just going to try and keep this informal as possible, so if people want to interrupt as we go through, then I think it'll be all right with that.
Oh yeah, please do.
I'll leave you to run it. Yeah. Cheers. All yours.
Okay, thank you for the introduction. So I will try to destabilize things a little bit more. But yeah, please feel free to ask questions. I mean, little point of going with having you lost halfway through. Anyway, so this is work with Georg Gottwald, who was here last week. So some of you might have met him. He's now in London. And then Kai Bergmann is a PhD student of mine. So I'm a mathematician, so I should put that plain out there. You will realize it through the talk. But I worked a lot with geophysicists. Actually started while I was in England. Started in '98. Also had some collaboration with the UK Met Office, some people from there. And so I continued with this when I returned to Germany. And in particular, I've been involved sort of from the sidelines on their new dynamic core they're developing. It's called ICON, from ICON Sahedro grid. So they try to get away from the traditional long lat grid and build a fairly homogeneous triangular grid over the sphere, and then possibly also some refinements near Europe or wherever you would like to have a more accurate prediction. And so this is still ongoing. I think it should become operational somewhere next year or the year after the latest. And as you're all aware, it's sort of Navier-Stokes, and of course it also includes moisture and everything. So once you have to work with meteorologists, you realize that this is quite remote from what we deal normally as mathematicians, where we think we have a differential equation and we discretize it and we talk about convergence, etc., etc. I mean, these are all discretizations that far away from, I think, rigorous mathematical justification. So, so I found this nice quote by George Box, who is a statistician. Actually, statisticians are a little bit more liberal about these sort of things. So he says models are wrong and some are useful. And I think that's certainly true, and it is probably even more true for climate models. And of course, you can go about this in different ways. I mean, you really try to make very precise statements about the errors, like we would normally do in numeric analysis. We try to get upper bounds, but these upper bounds are often so hopelessly bad in practice that they don't tell you too much. And so another way that has become quite popular in recent years, and again in the climatology community, I think is sort of pretty well accepted, that one way, at least conceptual first, is to say, these errors are somehow random variables and you try to characterize them one or another way. Of course, that's just pushing things into a different corner. It's not really a solution to any problem. It's just a conceptual thing. And then I also been recently getting involved in the data assimilation project of the DWD. I mean, they actually trying to develop some ensemble-based assimilation methods. And to that, I mean, of course, again, for the meteorologists among you, this is probably well accepted, but I was actually quite amazed to learn how much you can measure these days. I mean, all the data that's out there, and especially through satellite data. And we have, in Potsdam, we actually have a center, the Geoscience Research Center, Geoforschungszentrum. I mean, they do a lot of this. And so all observations are, of course, wrong too. If you say models are wrong, then you have to accept the point that observations are also wrong because they're measurement errors. And again, some of the observations are more useful than others, and you would like to get a sensible approach to this. And again, it's normally treated as random variables. And so putting it into sort of a more mathematical framework, so you deal with three big items. The first is sort of the model and its solutions and uncertainty caused by various approximations, could be through the state, parameters, model errors, etc., etc. And this is now becoming actually a very active field in mathematics or numerical analysis itself to quantify these model uncertainties. So there's methods like the stochastic collocation method where you say, I have an elliptic PDE and the diffusion constant is not known. It's just we have a probability density function, so it's actually a field variable, a random field. And then you try to find efficient numerical methods that can assess the spread, and you can compute expectation values over the solutions, induced solutions. So I'm not gonna talk about this very much. I'm just gonna assume that we can do it somehow. And then of course there's the second side. This is data that we have and measurement errors, and these are all very well linked with inverse problems. And there's of course a whole world out in inverse problems. And again, I somehow will not touch on this very much. Instead, I will look at the combination of the two, how you, given a model and a way of quantifying its uncertainty, and given data and a way of at least formulating the forward problem and its statistics, how can we combine both to get better predictions and quantification of the uncertainties coming out of both. And that's of course what's called data assimilation in geosciences. As a mathematician you would call it non-stationary inverse problems, and as a statistician you would call it filtering. And it's most often framed in a Bayesian framework. Okay, so let's move on to the mathematical statement. So we have a differential equation. So a model for me consists as it has a differential equation there, and it also the model is completed by also specifying boundary conditions and initial conditions. And so for the purpose of this talk, to keep simple things as simple as possible, we will assume that the equation itself, the evolution, is actually, there are no errors in there. Of course, that's very unrealistic, but just to keep things simple, we will assume that the model itself, the equation itself is correct, so there are no errors there. But the uncertainty comes through the imprecise specification of the initial state, or it could be boundary conditions as well. And so we will treat, according to the recipe I put out initially, saying any errors will be treated as random variables. So I will treat the initial condition as a random variable, given, and I will assume that there's some probability density function attached to it that describes the statistics of this random variable. So a PDF is a function that's non-negative and integrates out to 1, right? And so this, of course, implies that through this differential equation, then at any point in time, the solutions, we're not talking about a single solution, but about a whole set of solutions, then our family is again a random variable. And we want to characterize, the first step is then to characterize the PDF that arises at later times from the PDF at initial time. So again, for simplicity, I will stick to Rn, and I already said this here. So, of course, one important aspect is that we don't actually, often it's very hard to, just out of the blue to specify this. So this is a bit of a red herring. But in a way, it turns out that for most of the problems we will look at, it's relatively insensitive with respect to the initial PDF. So it will sort of calibrate itself eventually, unless you do some really stupid things here. Anyway, yeah?
Could the initial state, as you define it there, include unknown model parameters?
Yeah.
In principle?
Yeah, that's one way people deal with unknown parameters, that you would say, well, there's a lambda, and then you augment the system by lambda dot equal to 0.
Okay, right. Yeah.
It's one way to deal with it, right? It's not, I don't think it's, yeah, it's perfect, maybe not the perfect way. You might actually deal with the parameters in a different way, but for the purpose, yeah, just to say it's possible, this is one way to do it. So you add just a trivial differential equation, lambda dot equal to 0, and then yes, there would be a spread in the parameter values as well. Right. So So this is the side of the model, and the side of the observations. The approach is that what we really observe is y. So y is, let's say, the temperature in a particular, like in this room or something. And it will depend, of course, on the state of the atmosphere. So x is a state vector, so it's a complete description describing the complete state, let's say, of the atmosphere at this point. And you have a measurement, and this becomes a linear operator that maps the state into observation. Of course, we see this, and what we would like to know is, of course, this. And this is, of course, highly rank deficient, so you can't just invert it and bring it over to the other side. So that's why it's an ill-posed inverse problem. And on top of this, there are also measurement errors, of course, right? So it's noisy. So even if you were able to invert this operator, it would still not be the truth because of the noise. And the noise we assume to be, I mean, the measurement device should be unbiased, and there's some covariance matrix R involved. Okay, so and then the problem of data assimilation is to combine now the previous slide with this slide, and essentially get what we like to get is, as I said, somehow a best model at any time xt. We like to characterize the solutions as described by some PDF, depending on time, of course. So this is a PDF. All right, so that's what we like to find. Yeah?
How important is the Gaussianity
assumption? It's not, I mean, for the abstract formulation I will derive next, it's not essential.
Good.
Right?
I was thinking of those of us who live in the high desert plains and you're observing precipitation.
Yeah, right. Oh, yeah. So this is, of course, yeah. I mean, these variables they shouldn't be negative, right?
Right.
It's not a good idea. So, of course, you can then take log normal distributions. I think that's one way. It's not maybe perfect, but I mean, I think from what I understand, one popular way to deal with the situation is to transform it to a variable where it's then nearly Gaussian. That's one way, or you try to work directly with the precipitation variable. But then I think the PDF itself is probably not so problematic, but the non-negativity constraint that makes it a bit more difficult, right?
ECMWF have implemented quite a good way of doing this.
So as a transformed variable, or with?
It's called the home transform.
Yeah, right. So that's what I understand too. So that the preferred way at this point, I think, is trying to find a transformed variable, where then in the transformed variable it looks nearly Gaussian.
The other comments I make is that this sort of idea of the statistically optimal analysis, which this is trying to give you, although it's only rigorous for Gaussian distributions, and the idea that you believe the more accurate source of information is probably going to be true even if things aren't strictly Gaussian. So there's sort of principle behind all this, which is probably much more valid than the case.
Right, we're not yet at this point yet. Yeah, so you're jumping a little bit ahead here, because at this point we actually, I stay like, but it could be a nonlinear operator. It's not a I just put it down this way here, so it's a linear observation operator, but that's not essential at this point. It's also at this point actually not essential that it is Gaussian. The framework I will put out next is not related to this. Later on, when I talk about a particular method, then it is really very much tuned to the Gaussian assumption. But actually, the purpose of my work, or what I'm trying to, the layout I'm trying to give here, is actually exactly to get away from all these assumptions. That's the idea, if you ever get to this point. Yeah. Right. Yeah.
So you started off with this probability density function of initial conditions.
Yeah.
And now you're talking, so then you have a kind of possible solver trajectories. Now you're talking about observing a particular trajectory, are you?
No, this is not yet related. I mean, this axis here, let's say, this would be the truth, the real solution.
So we're thinking about a single trajectory which we know has been drawn from your distribution row of initial conditions.
No. The previous slide is one thing. Let's forget about the previous slide for a moment. So let's say we have the perfect solution.
You have
right?
a set of observations, you're saying. So that set of observations come from a particular realization.
Yeah, so but we assume that being the truth, let's say, right?
So that's the thing that's unique.
So if this were the truth, we can't see the truth. All we can see and learn about the truth is a measurement, so a small subset. Plus it's noisy. So there's noise on top of it. But this is sort of referring to the truth, let's say. The real state of the atmosphere, which we can't observe. Of course, eventually we will replace this then by ensembles of approximations to the truth we generate from the model.
Yeah, well, you'll still only have a set of observations drawn from the truth. Even if you're
Yeah, so it's the observations are still drawn from the truth, right? I mean, this is the observations are the truth plus noise. Okay, so how do we find this probability density function here? I mean, this ideal object that would describe all the knowledge we can have about the combined problem. So here, I mean, in filtering, there are different ways, of course, of looking at this. Some, especially in the mathematical literature, you find that you assume that the observations come in continuously in time. It's a continuous time problem, continuous time filtering. In geoscience, I think we more agree on the fact that it comes in at discrete times, and so it's an intermittent data assimilation problem. So where you have, for a while, you just have the model, and then at some point you say, now I have an observation, and at that point I have to combine the model with the observations.
I'm not sure that's really true these days with satellite data. I mean, no, it's not. They're not.
Yeah, that's an interesting question. I entirely agree, but
That's most of the data now. So
yes, right. I mean, I would actually, yeah. That's actually one thing that irritates me slightly with the current practice in these implementations, that sometimes you take a 3 hours window and you collect everything to 3 hours and then assimilate.
Yeah, we still have to work out the difference between the forecast and the observation at the correct time. So we have to put the continuity of the observations back in.
Yeah.
And that makes a big difference. I mean, everybody now realises they had to do that, and all the schemes that work well do that. So they do have to allow for that, otherwise you get big degradation.
Yeah. No, I entirely agree. But I think, let's put it this: most of the current, the state of the art at the moment is still that it's sort of treated continuously. I mean, discretely.
Well, you definitely, though it's sort of you definitely, in the state of the art, what's operational, you have to allow for the fact the observations can be at any time and compare them with the background at the right time.
Yeah, but the way you still, I mean, okay, you certainly compute cross covariances, but it's still, I think, what I understand from talking to the Canadian Met Office and others that run these things operational, you still have a 3 hour, 6 hour window when you actually assimilate.
Yeah, you have to chop the calculation up into bits because otherwise it's not practical. But when you do that, you have to recognise the observations not all at the same time.
Sure, yeah, you have to compute cross covariances, yeah, right. Yeah,
It's essential to do that.
Yeah, sure. Yeah, the Canadians also do it, yeah. But it's still, the fact that you change the model dynamics only at discrete points.
Just a question of what is that's more a question of what is practicable in terms of how you actually implement these ideas. So if you've got someone who gets away from that, that's nice, but that's why it's not quite the way you said it.
Right. Anyway, I mean, I would be happy to get away from this Windows thing. In fact, if we ever get to that point, I will have a slide on that. Anyway, so let's assume we still in this sort of we have a certain window where there's no observation. Then the evolution of a probability density function is just described by Liouville's equation, which, as you look at it, is actually just a continuity equation. So you can think of this as a fluid. Remember that our model was x dot equals f of x. So you can think of this like a velocity field, and f being the, in this case, prescribed function, just depending on the state. So this is, of course, very high dimensional. It's not like a three-dimensional fluid here. So this is n is very, very large. So this is a continuity equation in a very high dimensional phase space. But otherwise, it's really just a continuity equation. And so you plug in your initial, ideally you would just plug in the initial PDF and then solve this equation for some time, and then you get what's called the prior, in Bayesian statistics, the prior probability density function. That's the knowledge prior to, let's say, the measurement. And numerically, you could say, well, there are many ways to do this continuity equation. In fluids, of course, you would just build a grid, and then you would discretize it over a grid. Unfortunately, because of the dimension of this problem, this is not a viable approach, and then we actually will use Lagrangian methods, particle methods, for solving the Liaison equation. Anyway, that's already looking ahead a little bit. So anyway, so this is what we do whenever there's no observation. So we have a PDF, we evolve it in time in principle, and then get to the next point. So when there is a measurement, then we do Bayes' theorem, which we've seen, I think, probably a few times now. So that tells you, given this prior, so this is what we got from the model just before the measurement, the distribution of solutions. And this is the likelihood function. So the likelihood function is associated with this measurement. So remember, we assume that the difference between the truth, I mean the observed truth, and the actual observation is Gaussian distributed. So that's why I write this as a Gaussian distribution. Covariance matrix was assumed to be R, and there was no bias, so it's just this. So this is just a statement about the difference between what I would see if I could observe the truth directly and the thing that I can actually measure. And so it's a conditional probability of observing Y if I would know the truth, which of course I don't. All I know about the truth is actually this distribution. So I have to multiply these two things. So to get actually the reverse statement, what is the likelihood of saying, of observing X given Y? Okay, so this is a trivial calculation. It's just pointwise multiplication for each X, and then to get the next probability density function after the measurement, you just plug in your particular measurement you get from the observational people, and that reduces it again just to a function of X, because here it's still a function of X and Y, but then we have a particular realization of the measurement process, and we just plug it in there, right? So it's Bayes' theorem in this context, and that's then called the posterior PDF. So you make a jump, right? So whenever you have a measurement, the PDF jumps, and that's why I have a plus, let's say, T minus, this would be P or rho, the rho prior, and then I continue right after with the posterior. So that's why I have this plus and minus here, because of this continuous change whenever I have a measurement. So now the effect of this is generically, I mean, if I assume it's Gaussian, that let's say this is my prior PDF, the green one is the likelihood function, then one thing that's generically true, that the posterior has a smaller variance, so the uncertainty is reduced. That's what you assume. I mean, you put in more information than you had just from the prior alone, so it should be smaller. And then you also see that the most likely states, the maximum of these PDFs, for the posterior, it's a linear combination of the likelihood and the prior. And for example, if the likelihood is very narrow, then it will be tilted more towards the likelihood. If the prior is narrow, then it's tilted more towards the prior, because then you believe your prior more than your likelihood. So this is the whole delicate business about filtering, that you have to get pretty precise ideas how, relatively speaking, are the uncertainties in the likelihood, the measurement, and the model. So if the model is very accurate, then you will rely on the model, etc. So this is just, so that was just to warm up. Now let's talk about, so this is basically the theoretical problem statement. There's nothing more to it really at this point. So how we go about it in terms of numerics. I already said that the best way to do Liouville's equation at this point is really, so remember we have to propagate Liouville's equation. And there are many ways to do it numerically, but because it's so high dimensional, the popular approach at this point is a particle method. So you generate m solutions of your differential equation, and you draw the initial conditions from your initial probability density function. You can do it various ways. And then you just, because the model is to be, the equations are assumed to be exact, you can just solve these equations, and of course you replace it by a numerical approximation, time-stepping procedure. And so you get an evolving set of solutions, these ensemble members. And with them you can associate an empirical measure with some weights. So you might give, you can also give them non-equal weights. Of course, initially we would give them all equal weights. And so alpha would be 1 over m if you have m members. And that's actually an exact weak solution of Liouville's equation. This is Dirac delta. So you have little Dirac delta function moving around in phase space under the dynamics of the equations, and that's it. So now, when you come to assimilating data, then remember that Bayes' theorem was just boiling down to a multiplication, pointwise multiplication. So now you have these Dirac deltas and you have the likelihood multiplying with it. So it basically, what it boils down to then, you fix these Dirac deltas, they don't move, and instead you change the weight. And so a particle or an ensemble member that's close to an observation, to a y value, or for which, let's say, let's be more precise. So for each of these ensemble members, you can of course generate a pseudo observation. So if that were your truth, then you can just applying the observation operator to that ensemble member gives you an pseudo observation, and then you compare it, of course, to your true observation, and you weight all this by the likelihood function, this difference. And if this is small, then you will say, well, that particular solution has a high probability. And to represent this, it means that you change the weight, and so if this is close to 1, then the weight will not change much. And if one particular ensemble member is far away from the truth, then of course this difference will become large and the likelihood will become small, and then this will become, in the next step, the alpha will be small. So this is, theoretically, this is called a particle filter. But because of this reweighting, it's actually highly inefficient, because basically what happens is that some particles, or very few particles, will collect all the weight, and all the other particles will have 0 weight, essentially, and they will not contribute really to the statistics anymore. And then you do work that doesn't pay off in a way. And of course, the particle filter community is huge. It's also sequential Monte Carlo methods, sometimes called, and there are various fixes to this, of course, but we'll say a few words in a minute. Anyway, so this is the key step to do. So it's basically, you alternate, in a particle filter, you alternate between moving these ensemble members around under constant alpha. So if it's just the model, you don't change those, but you move the points around. And then whenever it comes to assimilation, you do something complementary to it. You don't move the points, you don't move the ensemble members, but you change the weight. All right? And so again, with the figure I showed you before, what basically happens on a particle filter, let's say this is your prior, these are the ensemble members, they all have equal weight. And then to get the posterior, we can, of course, because it's Gaussian, I can draw it, so this is a red curve, but to represent it in terms of your ensemble member, you're not moving these points, but you give them different weights. So for example, this is far away from the likelihood, so this gets very small weight, And these are more in agreement with the likelihood, so they get a larger weight, and then it's sort of transient in between. And you can imagine that if you do this several times, that only a few particles are left with a large line. Wait, of course you have to, the sum of the weights will always be to 1, so you have to normalize the weights in each step. Okay, so, and in practice, of course, as then what is done in practice, you say, in particle methods, you take this as an approximation to your PDF, and normally the red curve is not available to you. In the Gaussian case, I can draw it. But in general, this red curve here is not available, so all you know is this distribution of points with different weights. But then you fit the PDF to it and you resample to get, again, particles with equal weights, or ensemble members with equal weights. Unfortunately, this doesn't work in geophysical applications where we have, at least at present, it doesn't work. There are some nice survey articles in Monthly Weather Review appeared over the last 2 years on this issue. If the number of ensemble members is much smaller than the dimension of phase space, then this resampling seems to introduce too much statistical noise, and it's not reliable enough.
Sebastian, do the
Yep.
weights evolve continuously in the scheme? When is there a chance?
No, these are jumps in a way, right? So these weights, these are jumps because. So whenever whenever I switch on my model, the weights are actually constant.
Right.
So under the model dynamics, it's just constant weights, but the particles itself change location. But when you do an observation, I freeze the location, and I do this formula. So it could be an equal here, except for the normalization.
Right.
Right. So the jump in a way comes through this comparing the pseudo measurement that comes from saying, if this was my truth, then this is the observation coming from that truth, without noise, of course, and then comparing it with what you measure.
So you were saying earlier that the problem with this approach is you end up with, I guess, ensemble members that really aren't contributing to the statistics.
That's right.
And I guess that implies that you never get a situation where what was an outlier now becomes in the center of this distribution.
Well, of course it could happen, but imagine, I mean, basically what's wrong with this approach in this very naive setting, of course nobody would implement like this, is that basically, imagine what happens. I mean, you would do weather forecasting, right? You would say, at some point I have my little ensemble, solving ensemble. Now I use my model and I run it for a day. And then I look at the output. And then I give them different weights. And some will be good and some bad. And then for the second day, you do nothing. You just take the same forecasts and keep them going. Now, we all know that if you just would continue with using your model for a week, it's completely off. Right? And that's, I mean, you can't capture this with re-weighting anymore. Of course, you could hope that some forecast that was wrong for a week, the second week becomes correct again. Right? This would be your outlier suddenly become the truth again.
Yeah.
Right?
It doesn't allow for systematic drift, does it?
Say again?
You've got a systematic part of the error that stops that working.
Well, that's even worse. I mean, here in this idealized world, we even assume it's no systematic. But
Well, I said, well, the situation
in practice, it
right,
is systematic.
what
Yeah.
stops that process working.
Well, even if even if there would be no systematic drift, it's just the nature of the forecasting process that it's if you just let your model run and the model's also not accurate enough. I mean, that was all the work of Edward Lorenz, right? The saying basically there's no way you can use, you can just take a single trajectory or a few trajectories and hope that they will cover the weather for more than 5 days, let's say. So you have to do something about it. I mean, you have to, and one way is, as I said, to construct a PDF and then focus things in the area where there's a high likelihood, and then shoot off new trajectories from there, and then hope that this will capture it eventually. So then you have still enough ensemble members there that will keep close to the truth. Okay. So here's
Excuse me, just
yeah.
sorry, real quickly. So, is each of the at the point of observation, are you reinitializing all of the calculations, or are you simply propagating them forward from their initial condition previous to the observation?
That's what the particle filter would do. It's just propagating it forward from the previous forecast, so not reinitializing it. This is a naive implementation of the particle filter. You would continue exactly. This is exactly the problem. Right? You don't do a reinitialization. Right? And, but of course, as a mathematician, you can prove it converges, right? Just have enough particles, it will converge, right? So mathematically, it's all fine, but in practice, it doesn't work. So here's what an alternative view on this. So basically, what the problem behind this is that the dynamics formulation and the assimilation, they're not compatible in a numerical sense in a way. And we saw in the statistical model that one would evolve the positions of the ensemble members, whereas assimilation changes the weights. So these are complementary things. And you can actually think of this, if you fluid, I guess we're all here somehow knowledgeable about fluids, you switch between a Lagrangian or Eulerian view on fluid dynamics. That's basically what's happening. I mean, when you do assimilation, you switch to an Eulerian frame, and if you do dynamics, you do a Lagrangian frame, and you constantly switch forward and backwards between the two. So now things would get easier if we could stay on one side entirely, and that's basically what I try to show you in the next few slides, that in fact, we can think of assimilation as a Lagrangian fluid problem, or as a transportation problem. So we're going to reinterpret the assimilation step as, I mean, this discontinuous jump in the PDF during the assimilation. We're going to build a homotopy or an embedding that, I mean, it's going to be an artificial time because in real time it's instantaneous. But in this artificial time, it's going to look like a fluid problem. And that basically then means that we think of this as a reinitialization of the ensemble members, right? And then we eliminated the problem of reweighting, because then there's no reweighting anymore. We move the ensemble members in a precise way so that it matches the desired or the wanted posterior probability density function. So initially particles represent the prior, and so we're going to move them around so that they represent the posterior distribution. So you can think of this as having a heap of sand, that's the posterior, and you know from Bayes' theorem you have to transport it over there, that's the posterior distribution, the sand will be there. And then just in a transportation problem is a classic mathematical or practical problem for anyone who has a garden or anything, or has ever built a house, that you have to once in a while shovel the sand from one pile to another.
So now you are altering the ensemble members.
Now we're going to alter the ensemble members.
So that's the key thing you need to be
in a very, yeah, so you can actually state in a very precise way what you need to do for this. And last week I gave a talk at Imperial, and it turned out that Dan Christian, he's working on something very similar in the continuous filtering approach. So he's in the math department at Imperial, a pure mathematician. Very hard to read these papers actually, for me at least, as a mathematician. Anyway, so for notational purposes, we're gonna remember that the likelihood was the e to the minus L. So the likelihood function is e to the minus L. So I extract the exponent, the negative of the exponent. So it's called the negative log likelihood function for good reasons. So, and then we build this homotopy, right? I said I try to build a continuous embedding from here to here. So I have to describe a path how I'm going to put this pile of sand to the pile of sand over there. And the easiest way is to split up the e to the minus L into n bits, so n multiplications. And that means that the effective likelihood function is going to be minus L divided by n. Sorry. Right? N is just an integer. And so this is just because there's a normalization constant involved. So if that's why there's this proportional 2. But then here's equality, and so yeah. So and then I have to take the n-fold product of this, and then I just do a Taylor expansion. Right? There's nothing mysterious about it from there on, because if I have e to the minus L divided by n, and I introduce this incremental artificial time 1 over n, then this of course becomes proportional to 1 minus delta S L, approximately, as n goes to infinity. And I have to then also take care of the normalization. so that the integral should always stay 1, which means that if I take this limit, then I get a continuous deformation in this artificial time s, and s runs from 0 to 1. And this is the equation you get. So it's minus rho L, and this comes basically out of this expansion. First, you get like an Euler discretization of this. I mean, what you derive from this formal Taylor expansion there, and then probably should say maybe I should mention this. So I then rewrite this as an incremental process. So I say rho I plus 1 is rho I times e to the minus L divided by n. Rho naught is equal to rho prior. Rho n is equal to rho posterior. Right, so I now take incremental, and it's all Bayesian, right? So this is all a Bayesian step, except that I feed the data in incrementally. So this is like an incremental way of feeding the data in. And then I use this, and then you can already see that you get like an Euler discretization involving rho times L. And then you also have to take care of this normalization. That turns out it's just that you have to take the expectation of L with respect to rho. Expectation means nothing than the integral of L with respect to rho. And that's it. So this is embedding. Of course, that doesn't look like a fluid problem. In fact, it doesn't look like a PDE at all, because it's just pointwise multiplication here. The likelihood times rho at each point of x, and then of course everything is coupled together because it's an expectation there. So you actually have to know the solution everywhere to propagate the density. Otherwise, it would be just a pointwise multiplication in phase space.
But you want that to express the correlations in the problem, presumably. So
Yeah, sure. Yeah.
dependencies.
Well, this is this renormalization business. Yeah. So, for example, if you have two Gaussian distributions, I mean, if your rho looks like has two Gaussians, it's bimodal, then and you have an observation, then it's more than just multiplying the it's more than just multiplying the Gaussian with the likelihood, each contribution, but you also have to make sure that the integral balances out to 1 again. So, so that's what this does here. Right. Anyway, so that doesn't look like a Gaussian, like a fluid problem, but nothing prevents us from saying, why don't we just try to interpret it as a fluid problem? So we try to interpret the right hand side as to being derived from some, oops, why is this always moving here? Yet unknown velocity field G. Right? We don't know the G, but hopefully we find a solution. Now this is actually a problem that, yeah?
No, we're sorry. But what at this point stops you from saying that the the one on n, artificial time discretization, can now be applied back to the time step that you've used for the dynamics?
Yeah, well,
At which point you now know G, because it's F at each of your, fractional time steps, which you can approximate.
yeah, that's what we're eventually going to do.
Okay,
but not quite yet, because well, this is again. I mean, forget about this. It's just a normalization business. So this again is very much Eulerian. So this is what it means that you could easily implement this by just again changing the weights of each of these ensemble members,
Right.
and that's what we want to get away from. Because we have Liouville's equation that we need to solve somehow whenever we have just the equation. So we do this by moving these ensemble members around. And then if I would say, well, let's now just do this even incrementally, then it would just mean I still do the old thing, I mean, like in the polymer, except the weights would now follow a differential equation. I mean, so it would not be very exciting at this stage yet, because the differential equation you would avoid. So each weight would get a differential equation here, and would be alpha I times L, evaluated at the ensemble member. So it would be depending on xi on the observation if you, this is what the likelihood depends on. So now all we have, I mean it's a minus here, all we have achieved is now we have a differential equation in the way, so it's not a big deal. We still have the same problem. So what comes out of this naturally would be a differential equation, and alpha would, well, the dot is here a different dot, so it's ds, it's artificial time. So that doesn't help much, because we still keep the x fixed. So but exactly what we're going to do now is we're going to try to say this differential equation, we reinterpret now as not changing alpha, but moving the x, the ensemble members around. And to achieve this, we have to interpret the right-hand side so remember we have we have d rho ds, we said minus rho L minus expectation rho L, and we say somehow we want to find a vector field G, and then we can interpret this then has a natural interpretation of moving them in artificial time to ensemble members. And it moves them.
An artificial force.
It's like an artificial force, that's right. Yeah. It's like augmenting your model.
Mm-hmm.
Yeah. So this is optimal transportation is a big field, and that's sort of just borrowing one idea from this field, which is Felix Otto used actually in a sequence of very nice papers where he showed that like the heat equation can be shown interpreted as a gradient flow in some sort of space of densities. And so the norm he used is exactly what I use here, but let's not worry about this too much. So all I gotta, basically up there, G is, we can't solve for G because it's not uniquely determined. I mean, all G's, for example, that leave the flow field invariant, we could add this to a given solution. But to make it unique, you say I choose the one that minimizes the associated kinetic energy. So if you interpret G as introducing an x dot, so to speak, this is like a velocity field, and you minimize the kinetic energy to this here, and with the match matrix, you can set it to identity. You don't need to worry about this at this point. So mass, this is just a matrix given. You can choose it, and of course you minimize over all vector fields that satisfy the continuity equation. So this is bit of reverse engineering. We assume that this is given because we have it from, this comes from Bayes' theorem. We also know rho because it's the current probability density function. And so, we need to find the V, and we minimize this. It has a unique solution, and you can, a bit of variational, writing down the variational principle, doing the variational derivative, setting it equal to 0. It pops out that the G is then defined as a gradient of some potential. So you can generate this as a potential flow, a gradient of some cost function. And the cost function, guess what, depends of course on the likelihood function. Anyway.
Isn't this basically taking the dynamics and making it a weak constraint rather than a strong constraint?
No.
It's not
No.
using model dynamics at all.
The model is here is completely vanished at this point. It's not there.
But G is not F, and F is really the propagator. And
Yeah.
if F is not G, then you no longer have pure dynamics.
That's right. But we'll see it on the next transparency where the G comes in, and then you will see why it's not weak. It's not a weak constraint. Anyway, so you can write it this way, and then the whole assimilation picture now, you can have a nice integrated view on this. So you have, first of all, you have your model. Most of the time, you just have your model. And so this gives you x dot, and given this model, you also have Liouville's equation, which then drives around the PDF, probability density function. Now, whenever you have a measurement at tj, at discrete points in time, you have an augmentation of your model, as you just said. And it is actually a gradient flow, so it means it's sort of minimizing something. So psi is like a cost function. And the cost function is very closely related to the likelihood. So you will always try to increase your likelihood, observations, I mean, the Bayes theorem has a mission to increase your likelihood. But in a very balanced way, of course, because you not just do a steepest descent on the likelihood, because you have to take into account how well you believe your model. So it's a very delicate process, so it depends on rho itself. It's not just minimizing the likelihood function, so the current rho comes in. But this comes in an impulse. It's like a kick. So I write this as a Dirac delta, and that is exactly accounting for the fact that this happens instantaneous in an artificial time from 0 to 1. So now, if it would be a weak constraint, I believe it should be augmented all the time somehow, right?
There's different ways of implementing weak constraints.
Yeah.
You can implement the continuum. I mean, they're all equivalent. It's probably linear, but
yeah. So it would be something like coming in continuously, right?
Yeah, well, you can do it like that.
Yeah.
Particular continuous form, right?
Yeah.
It's okay.
Well, that's something. I mean, the weak constraint. I mean, actually, the weak constraint in the first place would be a noise at a Brownian, it's almost a noise term in here, right? So the model would become a stochastic model.
So what you're doing is altering.
That's one way to get a weak constraint. So saying that the model is actually augmented by a stochastic term. If it's if it's simple Gaussian, then a discrete Gaussian, and it would be a Brownian.
But what you're doing here is you're taking
motion term in there, then it doesn't commute with your continuous limit.
No, that again has nothing. You mean this limit here?
Yes.
Yeah. So that would become indeed. One would need to think a little bit more careful about this.
What you're doing here is you're taking each model trajectory and you're sort of replacing its velocity with something else. You want to bend it towards the observation, and you're doing that separately for each ensemble member using this method. So you're really putting in something systematic, not something random.
That's right. That's a systematic term. Yeah.
So in a sense, you could say it was a weak constraint, assuming there was a systematic error in the model, which would be a bit like one of ECMWF's approaches, or you could just say you're bending the model trajectory towards the observations.
I think at this point I would just say this is assuming it's not assuming as a weak model. It's a strong model, and if you were to model the weak model, the weak approach in the sense of augmenting it by a Brownian motion, then indeed there's the issue which you raised that how these things commute. I mean, if you can really still separate Brownian the Bayesian out, and certainly you can't in the continuous filtering column, then they really interact. But there also the measurement process is continuous in time, so I'm not sure where the problem comes from, so I would need to think about a little bit about this. Or if you could still separate it out and just add a noisy term here and the rest would still remain the same. But I wouldn't just say you can. I mean, we'll need to go through the math. But the continuous filtering problem is a bit, is yet still a bit different from this. So anyway, in this framework, it's just sort of augmenting the dynamics by an additional term, which you can now think of being almost like part of the model. It's data driven, and of course the next thing to mathematically you make this a modifier, so you spread out slightly, and then you have a very stiff. You have like a model driven by a sequence of very stiff contributions, and everything is closed by an elliptic PDE. So you can solve this using your ensembles now, and ensemble members by this are driven where they should be. They're driven to locations of high probability with respect to the likelihood, and this gives you an approximation to the PDF, and then you plug this approximation to the PDF in here, and you have to solve this elliptic problem, and of course that's that's still an elliptic problem, right? So in practice, what you will do is you replace this, you build a statistical model for your PDF. So the simplest, of course, is Gaussian. So if you say, I have an ensemble at point and assume it is Gaussian, then this becomes Gaussian, parameterized by the ensemble mean and covariance matrix. And then you solve it, you can actually solve it analytically, and what pops out, of course, is a Kalman filter. It should be, right? So there should be nothing else. But you can equally well now say, I approximate this by a Gaussian mixture, and you can still solve it, essentially, analytically. while the arrow function, which I guess you can deal with. And then even for that case, if you have a Gaussian mixture model, you can derive the psi. So you get the additional forcing terms. And actually, what it turns out is it becomes like for each Gaussian mixture, you get a contribution in psi in this potential that just corresponds to the Kalman filter. And then you get an additional contribution in psi that has to take care of the fact that one Gaussian heap might increase relative to the other because the one Gaussian is closer to the observation than the other. So one Gaussian will get more influence and the other get less. And of course, what that means that the particles that have been on this heap that had more influence before have to run over to the other side. So you get particles very quickly running over to the side, right? So they change side, right? They realize that they're on the wrong team, and they join the other team and now the winner, right? And these are the contributions you get in this psi for a mixture model. Okay, so now we basically up. I assume this is now, of course, personally I came the other way around. So I showed you now the abstract approach. But what, of course, I did initially, I looked at the ensemble Kalman filter, which comes out exactly in this framework if you make this a Gaussian. Then you get the psi, which gives you a continuous embedding for the ensemble Kalman filter. And that's, of course, what we did first, and only this came later, of course, right? As always, we reword, when we talk about mathematics, we reword the history and bring the abstract first, and then sometimes you don't even tell the audience how you actually got there.
So you're saying you presented as an optimal transport formulation, but what you're saying is that's just in practice that will be an ensemble Kalman filter with a particular interpretation. Is that what you're saying?
No, it's much more. I mean, it's just saying if I say I solve this problem under the assumption that this is Gaussian, then I get an ensemble Kalman filter. But if I assume it, but if I fit a different PDF. And that's where your question maybe comes in. If it's not Gaussian, if you say it has to be non-negative, I mean, there should be no negative values, for example.
Can you do it with a truncated Gaussian?
Yeah, why not? Sure. Then I will get, so I will just, say there are no negative values of x allowed. So the psi will be 0 there. And so I still, I solve it. I'm not sure if I can, if I then have to resort to numerical approximation for solving for the psi, but in principle, I can say this is now a PDF that just lives for positive values of x.
You're saying this is something more general than an ensemble Kalman.
Oh yeah. You can fit any, given any choice on your ensemble members, you can try to fit any statistical model to it, and then solve this problem, right? And Jeff Anderson actually has a nice recent paper in Monthly Weather Review where he actually shows that it's probably advantageous to work first in observation space, because then all these things, you can treat the observations sequentially because they're all uncorrelated, and then these all become scalar elliptic problems. So a 1D elliptic problem we can all solve with just integration, right? Of course, then the question arises, and that's not entirely clear also in the paper by Jeff Anderson, how you map then the increments in observation space to the increments in real space. But if you do this, at least if you follow this approach, then these all become elliptic problems, scalar elliptic problems in observation space, because if the observations are uncorrelated. Measurement errors are uncorrelated.
What's the boundary data on elliptic problem?
Well, for this here, it would be 0 at infinity, but if you work in a finite domain, then it would be 0 at 0. Let's say if it has to be non-negative, then the probability being at 0 should be 0. So I think these are zero Dirichlet boundary conditions.
We often observe no rain, so why should it be 0 at 0?
Okay, so with the rain, I haven't talked about this yet. You have to think about what is the appropriate boundary condition for your PDF. Let's put it this way. In this case, if you have a finite domain, if everything is over an infinite domain, and it's probably a fair assumption that at infinity it's 0, probability to be at infinity is 0. But if you have a boundary condition where at x0 the probability density function stops, it doesn't exist for negative values, then you might have a proper boundary condition. But
Well, that's why I was asking if you could do it with a truncated Gaussian. Because the thing is, if you say that your precipitation is related to ascent, and you have fluctuations in your vertical velocity, which might be Gaussian.
Right.
Okay, but you only get rain once the ascent is over a certain amount.
Right.
Then you could possibly see that the distribution of your rain might be a truncated Gaussian.
Yeah, but I mean, okay, so, but if you think about water content, right, as a variable we really, we're working with, let's put it this way, then,
But that's not what you observe.
yeah, well, yeah, but in general, we observe not directly state variables, right? But we still do the assimilation in state space.
Okay.
But,
Right.
I mean, this is all out, right? But as I said, I mean, yeah, okay. So, but as I just said, in Jeff Anderson's case, if he really works in observation space, then this would be a problem. Yeah. So.
If the elliptic problem comes from a mass transport problem, it's like the allocation map, which obviously has got well-posed boundary conditions.
Yeah.
Aspect it doesn't, that effectively determines the boundary condition straight away.
Right. Yeah.
So if it's equivalent to that, then you wouldn't have to add it. In fact, you're not allowed to add anything else.
Yeah. I mean, I'm pretty sure. Yeah. I mean, I'm pretty confident. I mean, the boundary problem can be solved out. In particular, since Bayes' theorem tells us actually what the PDF in the end should be, right? I mean, we're just constructing a different view on it.
I think if it's mass transport, then it will, which I think you said it is, then it should be just built in. You know, it'll be an allocation map, and that. No, you can't. All you said.
Well, in a way, this is a bit less even than the optimal transport problem, but because we already, in a way, prescribed a path from A to B.
Now, this is very like what Brenier was doing, by the way. He was trying to solve fluid dynamics, interpreting and sort of minimising path between the initial and the final state. So it's not the Cauchy problem of fluid dynamics. It's another problem.
Yeah,
You've
sure.
got lots of papers about this, which I think is exactly what you're talking
Yeah,
about.
yeah. It's actually I talked with Jan about this. Yeah, yeah.
Exactly like what he's doing.
Yeah. Yeah, no, I mean, we had quite a long discussion in overall about this, yeah, with Jan. Anyway, so I want to shortcut this now. I'm running out of time. I'm way over time now, actually. So this is ensemble Kalman filter. You can interpret it this way, and in this continuous embedding, you get a gradient flow. This is the only thing I will show you, and then we will stop. So if you look at this G you get from ensemble Kalman filter, then it's actually of that form. It's a gradient flow. It's preconditioned. So the mass matrix I introduced before, and I said, well, don't worry too much about it at this point. So this M in the ensemble Kalman filter turns out to be the covariance matrix, and the gradient just depends actually on the likelihood. So unfortunately, I changed notation here. I should really fix this. This is an L. This is a likelihood function evaluated at x bar and the ensemble mean and the individual ensemble member. So you basically, the potential depends on the weighting of the likelihood developed at the ensemble mean and the mean of the values of the likelihood function over the ensemble members. And then the gradient flow is really just, you take this as a potential, it depends on all the ensemble members, and you differentiate with respect to the each ensemble member. And of course, everything is coupled because the mean appears here, and it also coupled to the covariance matrix. And that's it. So this is ensemble Kalman filter in a continuous framework. Again, this is in this artificial time from 0 to 1. And you can also actually interpret Evanson's original proposal from 94 and then augmented later, corrected by this perturbed observation. And the perturbed observation actually, they mean that we add a SE, a noise term to it. Anyway, it's not important at this point. Again, we get sort of this augmented view. We can do localization. We can think of modifying it. Yeah, I think let's just go to the end. The summary. Okay, so I think that this is sort of a framework of thinking of more generalized filters by interpreting the assimilation step as a transport, so as actually doing yet another Liouville equation in an artificial time, which means that you augment your model by certain terms, which pretty much like nudging. It's just I think it's a more refined approach to nudging. Nudging is doing the same, right? Nudging, you also just add additional terms to the dynamics, but here you put it onto sort of a bit more firm statistical framework.
And the additional terms change all the model degrees of freedom. Thinking more of a real case where you have a very complicated model. Can you modify all the degrees of freedom of the model with this approach, or only some of them?
Well, in principle, we'll couple to all of them, right?
That's one of the things you need to be able to do. That's why I was asking the question.
Yeah, no, I mean, it's, well, in the ensemble Kalman filter, we all know that if you have m ensemble members, then you can only control directly m-1 directions. But then,
Lots more artificially with localization.
and then you do this localization to you actually fit a different Gaussian. It's not directly the ensemble generated covariance matrix, but a modified covariance matrix.
So that sort of thing will still be there or not?
Well, I mean, for the ensemble Kalman filter, it would still be there. I mean, you can't. I mean, it's a way of what you say. What do you fit as a statistical model? What is the appropriate statistical model? And it's not clear that just using the ensemble covariance matrix is the best choice. It's a natural choice, but there are many ways of doing it. On the other hand, I mean, what this also allows you to do, you can do rigorous error estimates in a way too, right? You can say, well, if I fit in here some model and I use a different one, and in particular, if I can't solve it analytically, as we do in elliptic PDEs, I mean, what are the errors introduced to this? I mean, so there's also a way of assessing the errors, at least theoretically. All right, run over time here.
Thank you very much. Yeah.